Okay, on to chapter 17, dealing with radioactivity and nuclear chemistry. Now, if you think of radioactivity and nuclear chemistry, many people, the first thing comes to mind are nuclear weapons, but there's much more to it than nuclear weapons. And one of the great things we use radioactivity for is nuclear medicine. So we can use radioactivity to diagnose and or treat diseases. So typically the diseases are cancers. As far as diagnosis, you can certainly use imaging radioactivity to image things. And what does it mean to be radioactive? Well, originally it was term radioactive was it had given off radio waves, but there's a lot more than just radio waves. There's much more dangerous gamma rays that come off from it. So radioactive is essentially an unstable nucleus. When you have a nucleus, the nucleus has most of the mass of the atom, and there's a bunch of positive charges in the center of in the nucleus, and these positive charges repel each other. And you have two things: you have the electrostatic repulsion of the nucleus, and then you have the nuclear strong attractive force between protons and protons, protons and neutrons, and neutrons and neutrons. And the strong nuclear force is stronger than the electrostatic repulsion. But if you get into certain circumstances where the repulsion is stronger than the strong force holding it in, then the nucleus is unstable and it's radioactive. So we will use these radioactive nuclei then to do things like image things in medicine. An example of this, for appendicitis, you can take antibodies and tag them with radiation, and then inject that into the patient, and then you can then see where it's going, and if the antibodies accumulate in the appendix, then you can say, oh, we got an infection there, and then it can also image the appendix and see things like how big it is and whatnot, and do this all without having to open the patient up. So it's a nice tool, right? So the idea here is that you can do imaging inside a patient without having to do surgery. So what is radioactivity? Mentioned before, it's an unstable nucleus, and the nucleus will then become stable, and it can become stable in various ways. Typically, it's emitting particles. You can also get metastable nuclei that emit gamma rays, but in general, thing is that the radiation is emitted to make the nucleus more stable. So here is the discovery of radioactivity. I'm not going to go over this too much because this is just the history, although it is fascinating. And here shows the manner in which he did it. So it was fascinating. Of course, he called it uronic waves. And these uronic rays, he noticed that of course there was some that these do change things, but it was actually radiation. Also, Marie Curie. Marie Curie is an amazing scientist. I cannot extol her any more than I can. You know, she earned 2 Nobel Prizes. So and invented or discovered 2 elements. Of course, she named a very dangerous one, polonium, after Poland, where she's from. We do have, if you might notice some of the names in the periodic table, like californium and berkelium and americium. You know, that those were named in part because of they were discovered at California, Berkeley, and that's where I went to school. So I like that. I like that it's on the periodic table. So, but she named it after that. She also named radium, and so not everything that's radioactive glows in the dark. It's very few things do, and radium is one of them. And they would then paint radium on dials on you can do it in compasses for fighter jets, and they used to do that. They also did it for wristwatches. And what's scary about it, and people thought this was really cool, but you could see this through your eyes being closed. So they were that, like, the radiation in some ways was that intense that the radiation could go through your eyelids and you could see them. So for me, that would scare me, but that people thought it was cool at the time. And there's a whole bunch. If you want to do a search for the Radium Girls, they're the ones that painted it, and they had some terrible exposures to radiation. And but that's an interesting story if you want to go down that rabbit hole. And so yeah, she won the Nobel Prize and shared it with her husband. They were an interesting couple. They would carry samples of radium in their pockets, and unbeknownst to everyone else, they had to have sores on their hips. And Pierre died prematurely. He got hit by a cart, and he just from both of them working in the lab around radiation, they became weak, and Pierre died pretty quickly because of that. And but they did have a daughter. So, well, they had two daughters, and I with this one of the daughters though won a Nobel Prize in 1935 as well. So talk about a powerhouse of a family there. Mom and dad both winning a Nobel Prize, mom winning 2 and daughter winning 1. Like, wow, that's amazing. So amazing couple there. So let's talk about the different types of radiation. So we already mentioned with Rutherford and with the atom and with the nuclear atom, and we found different types of emissions from radioactive atoms and tried to categorize them. And so here are the different types of radiation: alpha rays, beta rays, gamma rays, and positrons. So although we call them rays, I mean they're actually particles. Alpha particle is a helium nucleus, beta is an electron, gamma is a photon, and positron is it's antimatter. So it's an anti-electron. Antimatter is the same as matter except for the charge and the handedness of the spin. So we talked a little bit about spin before with electrons. Electrons, the magnetic field of the electron generally points overall in a certain direction at a given time. And it also follows what's known as the right-hand rule. The positrons, instead of negative, they're positive, and not only that, its spin follows the left-hand rule. It has to deal with the way that the magnetic fields orient itself. So the way it swirls, if you will, that would be in 2 dimensions, as of course is in 3. So that's if you want to know what difference between matter and antimatter are, and also positrons. And when matter meets antimatter, they annihilate each other and turn into energy. So positrons turn into gamma rays, anyways. So I already mentioned when nuclei are unstable, they will then try to become more stable. And also for smaller nuclei, there's usually neutrons, 1-to-1 neutron. But then as they get more massive, you need more neutrons, and that's because neutrons carry the strong force alongside them. They also don't have any charge, so they don't cause repulsion within the nucleus. But there are more things with these rules. Odd numbers of neutrons or odd numbers of protons, those tend to be less stable than even numbers. So the even number of protons and neutrons are much more stable. It's like a full shell in electrons. And protons and neutrons, they have wave functions and they have energy levels just like electrons do. But their energy levels are so huge. Like electrons are pretty close together, but in the nucleus, the difference in energy are so huge they don't interact with each other. So honestly, nuclear chemistry is a lot easier than regular chemistry. At least if you're doing the quantum mechanical calculations, it's so much easier to do these things. So it's pretty nice, actually. So let's we mentioned this before in an earlier chapter about this. We have the chemical symbol X, and then the atomic number in the bottom. Although the atomic number and the chemical symbol are they are redundant, although we typically use them in nuclear. We do in nuclear equations, because in nuclear equations and balancing them is really easy. The top numbers and the bottom numbers have to be the same. So, and the top numbers is the total number of mass. The bottom numbers are the numbers of positive charge, or just the number of charge in general. So the top number, the mass number, is the number of protons plus the number of neutrons. And so then a couple of symbols. A proton has a mass of 1 and a charge of 1. So 1's on the top and 1 on the bottom for the charge. Neutrons have no charge, has 0 on the bottom and a mass of 1. And although a neutron is slightly more massive than a proton, we kind of, and now of course, depending on the nucleus that the proton or neutron is in, it has a different mass. We kind of just ignore the differences there and keep it there to the whole numbers. You look at electrons, for instance. Electrons and positrons are going to be considered to have no mass. I mean, they're about 1/2000th that of a proton or neutron, but we just kind of say it's negligible. Electrons do have mass. It has a mass of 9.11 times 10 to the minus 31 kilograms, at least, as a free electron. So it does have a mass, but we don't really we don't really consider that in these. Electron does have a -1 charge, and -1, just like the +1 for proton, and that's the 1.6 times 10 to the minus 19 coulomb. That's the charge of an electron or proton, respectively. So let's talk about the different types of radiation. The first one is alpha radiation. And alpha radiation is a helium nucleus. And what happens when something releases an alpha particle, it decreases its atomic number by 2, and it decreases mass by 4. And when we do nuclear equations, these are real easy to balance. So the top numbers have to be the same, that's the total mass, and the bottom numbers, that's the charge, has to be the same. So if you look at here, uranium-238, element number 92, so 238 is the mass number, 92 is the bottom, and also the U and the 92 are redundant, but we like to keep them together. And it alpha decays to thorium-234 and an alpha particle. And if you notice the top numbers, 238 equals 234 plus 4, and the bottom numbers, 92 equals 90 plus 2. So the top numbers are the same, the bottom are the same on both sides of the equation. And in a decay reaction here, we say it's the parent nuclide and then the daughter. So we only give daughters. So everything is a daughter in nuclear chemistry. So we consider that. So if you wonder where all these daughters, we only give daughters in nuclear chemistry. I kind of like that. I think it's kind of funny. And so nuclide, it means a specific isotope, and so that you're just determining like what the mass number, how many protons and neutrons you have. And so whenever the number of protons changes, the element changes. So in nuclear chemistry, we do change the element. I know in normal chemistry, we talk about when chemical reactions happen, we exchange atoms, and the atoms retain their identity. Nuclear chemistry is different. When we undergo a nuclear reaction, unless it's just the emission of a gamma particle, it's going to be it's going to change an element. So, all right. So I already mentioned there with how they balance the nuclear equations. So how do we do this? So thorium then is to decompose into further is gonna alpha decay, and now we have to know what the symbol is. So we're gonna lose 2, so it's going to be 88, and then the mass number is 228. So because it's 232 minus 4 is 288, and of course 90 minus 2 is 88. So we just have to look in the periodic table to see what element number 88 is, and it's radium. So that's what you have to do, is look at the periodic table and find whatever element number 88 is. So what is so dangerous about radiation? Radiation is ionized. It's an ionizing radiation. It creates ions. And how do you create ions? you rip off electrons. So that's how you create ions. You rip off electrons, and then in doing so, you can break bonds. And different types of radiation depends on where they're at and what damage can do. So some of the problem with this is that the cells, you can damage things like in our DNA has a backup code on it. So we have so if there's damage to the DNA molecule, the body can fix it, but sometimes it fixes it abnormally. It can lead to cancer. But the truth of the matter is, usually radiation just causes destruction and cell death. So I mean, radiation sickness, it's just your cells have died a lot, and you can kind of feel that when you're sick. One of our innate responses to being sick is when cells they'll commit suicide. They'll die to prevent themselves from propagating the virus, and that can cause a lot of the pain and suffering, like if you have a respiratory illness or something like that. So instead of the cells doing it themselves, though, you have outside things coming in and damaging it. So it can, and we'll talk about radiation sickness in a little bit. And also, it also depends on the ability for the radiation to ionize is its ionizing power, and the penetrating power is how far it can go. So some things don't have very strong penetrating power, some have very powerful penetrating power. So alpha radiation is a semi-truck of radioactivity. It's really massive. It doesn't penetrate very far. It doesn't go very far. I tend to think of it more like a pinball. Like if you've seen the old pinball machines and you pop it and then you have the pinball bouncing all around. This is what alpha can do. If it's inside the body, it's horrible. It's absolutely horrible. Like if you get radon in your lungs, the alpha particles can ping around your lungs, causing damage to wherever it hits, and that's very bad. If it's outside of your body, it doesn't go very far. It doesn't really. It might maybe goes a few inches in the air, and it maybe it won't even get past your skin. So I mean, alpha is not that dangerous. It's not dangerous at all unless it's in your body. So it's very, very safe. Although we'll talk about later, and it's not mentioned in the book, but whenever there's a nuclear reaction, nuclear event, a gamma ray is emitted. So gamma is always happens. So whenever there's a radioactive event, gamma rays are also produced. So you're not going to have a situation where just an alpha particle is produced. There's an alpha and at least one gamma ray. So, and as mentioned there, if you eat or inhale alpha emitters, these can be really dangerous. But outside the body, it's not a big deal at all. So beta radiation, it's an ejected electron. So neutrons will emit electrons via beta decay. And that will also go and then the atomic number will increase by 1. So a neutron can turn into a proton and an electron, and the electron is typically ejected from the atom and with lots of energy, and also gamma ray. So a beta particle is just an electron. So in the relative mass of 0, and the -1, that's the relative charge. And so, for instance, here, radium can beta decay into actinium and a beta particle. So you can see here, same thing is true. The top numbers and the bottom numbers are the same. So 228, both sides of the equation, 88 for the mass number of radium, 89 for actinium. But then you have the -1 from the electron. So you can see that the charge is balanced. They're both 88 on both sides. So the beta particle, it depends on where you have these. These are a little more dangerous. It also depends on the context. They're not too bad. There are certain, your eyes are a little sensitive to them. So you can get cataracts from beta particles. So, and one of the things that stops them is plastic. So, I mean, having a pair of safety glasses on usually stops beta particles. So it's not that bad. So it's so metal or a piece of wood. Frequently we use like anodized aluminum. That's very common for that. It's just a little little thick black thing of aluminum. So, and the inside the body as well, the beta emitter is not as nearly as damaging as an alpha emitter. So a little more dangerous outside the body, a little safer inside the body. So it's kind of your mid-sized car. I like the book with its descriptions here. Then there's gamma rays. Gamma rays is just, it's electromagnetic radiation. It's really high energy electromagnetic radiation. And the danger of gamma rays, they're ionizing. And if they hit an electron, it ejects the electron. So ultraviolet light will ionize valence electrons. X-rays will ionize valence and core electrons. And gamma rays can ionize valence core and it's pretty much any electron. There's way more energy in a gamma ray than any transition, electronic transition. So nuclear transitions are so much more powerful than electronic transitions. So gamma rays can just rip off any electron. And under certain circumstances, gamma rays are safer than other types of radiation like X-rays or even UV light. Because it's very common that the gamma rays just go right through you. They don't typically get stopped, but they are still dangerous. You don't want to get bombarded. It's a game of chance because the gamma rays might hit the electrons. So it just depends. So gamma ray has no mass, no charge. And so, for instance, and I mentioned there that whenever you have a nuclear transition, you're going to have a gamma ray. They always come in like, and there's any types of radiation, gamma is emitted as well, and that's the lowercase Greek letter gamma, so alpha, beta, gamma. So that's lowercase gamma. And so then the motorbikes of light radioactivity, they have very high, the ions and power. They tend not to ionize because they zip around so fast. They usually just go through everything, but they have the highest penetrating power. So you need like a foot of lead to stop them, or like meters of concrete. So like if you look at nuclear power plants, we have meters of concrete around them, and that's contain the gamma rays. Another type, positron emission. So in this case, a proton can turn into a neutron and emit a positron. And then it's very easy to find positrons because they have a very characteristic gamma ray that comes from them, because when it meets an electron, they annihilate each other. So it's really easy to find positrons. Positron emission, and there's another type of radiation not included in the book. It's called electron capture, and it actually is the same. It does the same thing as a positron emission, but you don't see the characteristic gamma particle from. And I'm using the word particle because it's a photon. Photons are also particles. I know it might be confusing that I use those terminology, but it's a photon, and we can describe photons as particles. So if you notice, we say alpha rays, alpha particles. So you can do the same thing with light. And I guess gamma rays are not light, but they're electromagnetic radiation. So you can refer to them as particles. So it is proper, and I know I'm not being consistent through here, but it's proper. So for instance, here you can have a carbon 10 nucleus go to a boron 10 nucleus, and this is what we use for PET scans, the positron emission topography. That's what a PET scan is. So positron is just like an electron, but it's a +1. Also, they had this a spin, which I mentioned before, but it's not. You're not going to see this. So, for instance, here, 30 phosphorus going to 30 silicon plus a positron, and the same thing. The top numbers and the bottom numbers are balanced out. And of course, there's going to be an alpha particle emitted as well. So, not alpha. Alpha particle. I'm sorry, a gamma. A gamma ray is going to come out as well. Also, the positron is going to turn into a gamma. So, summarize: alpha particles. They're helium nuclei. They have very high ionizing power, but they don't penetrate very far. Beta particles are electrons. They're intermediate for both. So positron is going to be similar to a beta, but the thing is, positrons turn into gamma, and gamma rays have very low ionization. I shouldn't say very low; it's low in general, but they have high penetrating power. So here's a picture of these. So here's the alpha particle, uh, beta particle, uh, gamma ray, and positron, of course. Positron is also going to turn the positron doesn't go very far because there's a lot of electrons around, and when they meet an electron, they annihilate each other and turn into gamma rays, anyways. So you don't see too many free positrons flying around. There's much more matter than antimatter in the universe. Even when antimatter is created, it's and the fact that there's so much more matter, it gets destroyed pretty quickly. So how do you find radioactivity? The dosimeters. So those are the badges that people wear. You can also, certain people can wear rings on their fingers. And if you've seen the James Bond film Dr. No, he called them radiation shields. And a lot of people thought that they actually shield you from radiation, and they don't. They just measure how much radiation you have, and then you develop the film, and then you see how much radiation you've had. There's a Geiger-Muller counter. We usually say Geiger counter. You have a cylinder of gas. It's usually argon, and then if and it detects gamma. So the gamma particle comes in and ionizes the argon atoms, and so it rips off the electron, and then you have a detector in there, and it detects the charged particles, and you hear the clicking sound, the more clicks, from that, and that's what people associate with the radiation. So that's the clicking device there. There's another one called a scintillation counter. Use material like sodium iodide or cesium iodide that flashes. It produces like a flash in response to energetic particles. And then you can collect these flashes and then get it into a meter, and then you can digitize. You can digitize many of these other, but very frequently when you have a digitized radiation device, it's usually a scintillation counter. You can do it for the other ones too, like the film. When you get the film batches, when they are developed, it'll be turned into digital data. And you can also you can output the count from the Geiger counters, so you can digitize those. But typically, the digital ones are scintillations. So we do have quite a bit of natural reactivity. Every single element beyond bismuth, and even this is debatable. Bismuth is considered to be maybe unstable, but that's if you want to dive down that rabbit hole, you can look into it. But lead and maybe bismuth is the end of the stability of nuclei. Everything heavier than bismuth is radioactive, and which means it's unstable. So and there are some of these here on Earth. So also there's a little bit of radiation in various things. So potassium, for instance, there are some isotopes of potassium that are slightly reactive. We'll talk about carbon, so a little bit of radioactive carbon, and also from space, including the sun. You can get radiation. If you're flying in an airplane, for instance, you actually, and especially during the day, you get a little bit more radiation because the atmosphere protects us from radiation. So we're resilient to radiation. But to a certain amount. If you get more, it can cause some problems. Also, maybe you've heard about half-life. So half-life, this is the amount of time it takes for half of the whatever substances it is to decompose. And honestly, nuclear decay it's a game of chance. It's actually it's probability, but it's just probability. But then when you're dealing with big numbers, like 6.02 times 10 to the 23rd or something, it follows a very predictable path together. So, but half-life. So after two half-lives, it's not they don't add together to form a full life. A half-life goes to one half, and then half of the half-life goes to a quarter, and then after another half-life, it's 1/8, and 1/16, and so on. So it's one half raised to the power of whatever number half-lives you had. So it's one over n to that. So keep that in mind with half-lives. So for instance here, thorium-232 has a half-life of 14 billion years. And so if you look at this, if you start off with a million atoms, after 14 billion years, you're going to have half of a million, and so on. You keep on going down. So, of course, the universe is not even 14 billion years old. So we haven't yet seen, we can't look 60 billion years into the future, or at least we haven't, because I don't know if we consider young or old for the universe. So let's look at this. So after one half-life, you've gone down to a half. After a second half-life, you go down a quarter. Well, let's look at a different nuclide like radium-220. It has a half-life of 1 minute. So you can see here, thorium has a half-life, longer than the age of the universe right now. So thorium sticks around for a while. And then radon, has a half-life of only a minute. So, there's been about 30 half-lives out of what have gone since you started listening to this video, for radon. So radon can decompose much more quickly. And here are some of the examples of the half-life and then the type of decay that happens with them. You can see there's some that are very quick and some that are very short, and it just depends. And I might tell you some of the things you might notice that when you have the odd numbers, if you see here that the thorium-219 has got the really short one, and it's partially because of the odd number there, an odd number of neutrons. So also there's nuclear decay series. So this one here, uranium is the heaviest naturally occurring element. So this again is debatable. Darlene Hoffman found plutonium in nature, so you can argue this, but sure, we'll go with what the textbook says. And it goes to uranium-234, and it eventually goes to lead. So it decomposes, and this is the series it goes, and it goes through alpha and beta decay, and eventually it gets down to lead-206. So so that means much of the lead on Earth has come from the decomposition of uranium, and we see these in various amounts. And so, if you wondered how we get the age of the Earth being 4.6 billion years old, we get that from these studies that's showing the decay series of the different elements. And it's not just uranium, thorium cycle is one. Potassium is another cycle, because potassium has a half-life of 1 billion years as well. So we can see so it's verified by other series as well. So here is the decay series. Start with uranium-238 and alpha decay, and then you see beta, and then alpha on down to lead, and then it goes through a series of alpha and beta decays eventually into lead-206, which is stable. And radon is one of the naturally occurring decay series of the uranium-thorium decay series. And if there's uranium in the ground, there's going to be radon as well. And it's one of the largest sources of human, well, at least natural radiation exposure, and it has a half-life of 3.8 days. So, and it's the exposure is typically to the lungs. So the lungs get quite a bit. And it depends on where you live. So you can see where the red area is. There's quite a bit more radon, and so that means there's more uranium there as well. So it's one way to find uranium, and it's also why people, especially in the Midwest, have to make sure their basements are it'll collect typically in the basement. So keeping ventilation will help get rid of the radon. With the half-lives, so since I told you the half-life is something that's well understood and very easily predictable, we can date things. So we can date the Earth like we have with potassium and uranium for the date of the Earth. We can also look at things that are alive, and a very common one is carbon dating, and it's carbon-14. And carbon-14 is made naturally, and it's made naturally by a neutron bombardment from the sun. And it forms a little bit of carbon-14. And the idea is, as the sun has been shining and with the carbon cycle, that there's a certain amount of carbon that is radioactive, and it's been sitting around, and that this rate of generation of carbon-14 has more or less been consistent. And also, although I might add, due to nuclear power and nuclear weapons testing, we've added more carbon-14 to the environment, so this has actually changed. But throughout history, before the 1940s, that was the same. So carbon dating won't really work for us than it will for the things. But before 1940, you can. And carbon-14 decays via beta decay to nitrogen-14, and a half-life of 5,715 years. So knowing this, then we can, and knowing how much activity there is of something, we can date it using the activity of and it's easy to find the activity because radiation is real easy to find. So it's really, really easy to find radiation. And but the idea is when you're living, you're eating. If you're a plant, you're photosynthesizing. If you're an animal, you're eating plants. You're eating animals. You're eating other animals that eat plants, and pretty much more or less the living creatures have about the same amount of carbon-14 in them. But then when the organism dies, it's no longer incorporating more carbon into their systems, and then the carbon-14 just decays. And so then when you find something that's no longer alive, no longer replaced, and you can date it to see how long it's been sitting there from the time of its death. And so for many anthropogenic things, so human caused, there's lots of things that we're living, papyrus wood and animal skins, so we can date these. And for instance, if the activity of something that is 50% of what it should be, we know that it's exactly then or near to 5,715 years old. So and if it was 25%, we would know it's 11,430. There are other ways to do it. The math, we can do it in numbers that are not necessarily half-lives. You can do this pretty easily using some calculus, but we're not going to teach that in this class. So there are ways to do this other than the whole half-lives. So to give you an idea, so the relative amount of carbon-14, and then with the half-lives and the simple half-lives there, that's the ages there. So one of the ideas, there was the Shroud of Turin that had an image of someone. They thought it was Jesus Christ, but then they did some radiocarbon dating on the shroud, and they found out that it was actually created in 1325 Common Era. So, and it's not 100% reliable, but it's pretty close. It deals with probability, and when you deal with probability of big numbers, when you're dealing with moles of carbon, although I don't think they gave them a mole from this, it was a small amount, but still you're dealing with huge numbers of atoms. It's a pretty reliable test. So let's move on and talk about nuclear fission. And maybe if you've seen the movie Oppenheimer, you might know a lot of this already. So Enrico Fermi, he tried to do this, and actually it was later further done more with Glenn Seaborg, but they discovered plutonium, and it's interesting. They knew it was dangerous, so when they discovered this, they knew we can turn this into a bomb, and they called it copper. So in their books, they would always refer to plutonium as copper, and if they used the copper, like the element copper, they would call it honest to God copper. So that's how they got around that. So that was their code word for plutonium was copper. But that was this is when they discovered this, and of course they later on use it to make nuclear weapons. So and but the Fermi found like, oh, these are electrons, so maybe we made another a proton. So yeah, Fermi never did it, but yeah, the good old folks at Berkeley did. So, but the idea though was to take uranium and bombard it with neutrons, and here's some more history. So the folks in Germany, they performed careful analysis of the products, and they found they found that the atom was splitting. They sound like, oh, we are fizzing the atom, and so we've named a couple of them. Fermium and Meitnernium is named after some of the discoveries here. So so Miter, Strassmann, and Hahn, they found like, oh, we've discovered nuclear fission. The way this works, it's a neutron, and like we call it the liquid drop model. It's like a little tiny drop, and it hits the nucleus, and it excites the nucleus, and the nucleus splits. It doesn't always split into barium and krypton. It goes into various products, but each of the nuclear reactions generally produce 2 or 3 neutrons, and then because of that, you can have a chain reaction. So, the neutrons are produced. They have to be slow. We call them thermal neutrons. So you typically have to have a medium that moderates it, and that's that makes sure that you don't have fast neutrons, for instance, and they slow them down. So uranium-235, it's about 0.7% of naturally occurring uranium. We have to enrich it, and you enrich it, and you have to enrich it to a very high amount. And each nuclear reaction produces 2 or 3 neutrons, which then can cause a chain reaction. So it depends on where you're at as far as the enrichment. For nuclear power plants, Canada doesn't enrich their uranium. They typically just use heavy water as their moderator. Here in the United States, we typically enrich it to maybe as high as 9%, sometimes 3 to high. It just depends on the nuclear reactor. We're kind of weird here in the United States. We haven't agreed on a single type of reactor. Each reactor is uniquely built. So here's the history of the atomic bomb. It's a wonderful story, but I think we've already had a Hollywood movie on this. So if you want to learn more, you can go and watch the movie, and of course led by John Robert Oppenheimer. So, and then had the Trinity blast. And then its use, the bomb's uses in Hiroshima and Nagasaki. So, and of course, we're familiar with the characteristic mushroom cloud. So I hope you don't mind me zooming through this, but I know that, although I think it's a fascinating story, but I think that the story is better told in the cinema. So, we do other things besides use uranium and plutonium to make bombs. We can also use it to make electricity. So nuclear power plants use nuclear reactions, and they generate heat. And you can use it. This is partially true. The last point here, the heat is used to boil water, generating steam. It depends on the reactor. You can have, that's called a boiling water reactor. You can also use a pressurized water reactor. It really just depends. We use both in the United States. Of course, the Navy especially uses nuclear power to power the submarines and also the aircraft carriers. That's the main power source of those vessels. But this is a generalized view of a nuclear reactor. And you have the core, which is it's a pile, and some of these words come from the original nuclear reactor in Fermilab, and the pile is literally a pile of uranium oxide, and then you have the control rods, and actually the failsafe is for the control rods to go down, and this is called the axe, and literally you had a guy with a bunch of control rods hanging by ropes, and he was standing there with an axe. And if they said axe, the guy's job was to cut the rope with the axe, and then the control rods go in the down in the in the nuclear reactor. This here, as written, this is a pressurized water reactor. You can have previously in the previous slide it described a boiling water reactor, but this is a pressurized water reactor, and you keep the water in the core. If you we tend to in the United States we tend to keep our nuclear reactors relatively cool, so we keep them about 500 degrees Celsius. So a candle flame is hotter than a nuclear reactor. So, but the thing is, I mean, this big block of uranium, though, it's at 500 degrees Celsius, and it keeps on putting out all that energy. So actually, this is a lot of energy it puts out, but we tend not to like to heat them up too high. We can, and how do you do that? Well, you can enrich the uranium more, or you can let the control rods out, and it can get really hot. So hot that it can melt the casings, and that's known as a meltdown. So we try not to keep them too hot, though, and we also keep everything as much in a closed system as we can. So steam moving, it can turn a turbine, and the turbine can turn a generator. If you're wondering, so turbine is just a fan blade, and then it puts a motor in a generator. Generator is just some magnets that circle a wire, and then that induces current flow in the wire. It's the same way that your alternator works in your car, so it's the same idea there. But that's generally speaking how we generate power for most things is via a generator. There's other ways you can generate power, photovoltaics do it a little differently. They use the photons, the sunlight turns into current flow from that. But generally speaking, we use generators and turning the fan blades to turn a generator. So that's very common. And of course, this is for a nuclear power plant, and Navy might also use this besides electricity, also as propulsion, for the vessels, so to propel them in the water. So it depends. We say 3.5%. It depends on the reactor. It can go up to 9. We tend not to enrich it too high, though, because we don't like to have a really hot nuclear reactor. So we like to keep it cooler. And we say the nuclear we shut it down when we put the fuel rods only back in. But the thing is radioactive in the term for radioactive is called hot. And one thing about even if a reactor is hot is off, it's still radioactive, which means still generate a lot of heat. And so this can be a dangerous thing. And this was also dangerous in the Russia-Ukraine war, because of the nuclear power plants there. Luckily, they turned the nuclear power plants off, and they cooled enough down that they're not as dangerous anymore. So, the war there is still going on as I record this video. I don't know how this is going to date further on, but yeah, the control rods they do stop the nuclear chain reaction, and they can also change the energy output of the core. So this is the view of a core going down. You can see that blue light. That's called Cherenkov radiation. That's when electrons hit water. And so if you see this, don't go swimming in the water. So this is something you don't want to do. So it's a little dangerous. But you see that blue water. I've never looked into a nuclear reactor, so I don't know what it looks like, but that it does have that characteristic blue water. So one of the major nuclear power accidents was Chernobyl, and also a great miniseries, right, if you've got HBO, and there was a catastrophic explosion. They were doing a safety experiment, disable some of the safety features, and then it blew up. So, of course, it didn't blow up in terms of a nuclear detonation, but it was a chemical detonation. But then it still was releasing radiation. The reactor was still on and released a huge amount of radiation into the atmosphere. And we in the United States, though, we don't have any graphite reactors. All of ours, they're all based off of water, at least the civilian ones. And the reason for that is that the U.S. Navy kind of pushed it's we have the same type. We use water as our moderator for that, and pretty much all of our nuclear reactors are like that. So we're not going to have the similar thing. We also contain our nuclear reactors in pretty thick concrete. Although there was the Fukushima plant, there with the huge earthquake though, and caused the cooling pumps to fail, so that it did turn off. Like so, this is not nearly as bad as Chernobyl, but the reactor did shut off. But the problem without the coolant, so that it's still like really hot. And what happened? There was so much heat that water, H2O water, turned into hydrogen and oxygen, and that later then triggered an explosion which broke away. And there was enough heat that there was at least a partial, it's hard to say, partial or complete meltdown, which means that the casing within the nuclear fuel melted. And then it released some radiation into the atmosphere. And so, I mean, of course, there's still some issues there. So, this caused lots of things. So, but the radiation release is not nearly as dangerous as it was with Chernobyl. Although I mean, this is not a good thing. I'm not saying, oh, it's not a big deal. It's a big deal, but it's just not. It's significantly lower than Chernobyl. And we're going to continue to clean this up for many, many years. And so that's one of the issues with nuclear power plants is like the disasters, if they happen, they're horrible. So some problems with nuclear power, waste disposal. Right now, we just take all the waste on site. Nuclear power plants, though, we generate about a car, like a car-sized amount of spent nuclear fuel. And so the nuclear power plants just have to manage that and keep that on site. We were thinking about centralizing it to Yucca Mountain, but this has had quite a bit of controversy, and we currently do not centralize our waste. Our waste is all done in-house with each nuclear power plant. So nuclear fission is breaking things apart. Nuclear fusion, though, this is taking two smaller nuclei and making a heavier one. So generally speaking, this is how the sun generates its power. It actually generates something called it's a carbon-12 star. It actually uses carbon-12 as a nuclear catalyst to form helium from hydrogen. It can form helium from a collision of four hydrogens, but it's not typically done that way. And so stars burn via nuclear fusion. Nuclear fusion is also used for hydrogen bombs, and hydrogen bombs are also called thermonuclear bombs because you need a lot of activation energy to make this reaction happen. And this is a general reaction. There's other reactions too. You can have lithium react with hydrogen to form beryllium, and that was actually a miscalculation for the first hydrogen bomb. The yield was bigger than they thought, and it's because there's other side reactions going on. So deuterium is heavy hydrogen, and tritium, the radioactive hydrogen, react to form helium form and a neutron. And the neutron coming from this reaction is very fast. So this one, it's not a thermal neutron. So this fast neutron can do some other things. It can actually split apart other atoms. It can actually split apart uranium-238, for instance. But you need a lot of energy for them, and we usually have they're called thermonuclear bombs because you have a smaller bomb that triggers the activation energy for the bigger bomb. So they're multiple stage weapons. And we would like to use nuclear fusion to make electric power. We're trying a bunch of different things. There's the National Ignition Facility in Livermore that's trying to do this via lasers to compress things down. There's tokamaks. We haven't quite figured it out yet. We're trying. We're absolutely trying, but we haven't quite figured out yet how to do this. It would be nice, though. So what happens with radiation? So acute radiation damage. So acute means short term. And Where do you get these? So you can get them from nuclear weapons or from nuclear reactors. Is where a lot of so people that were in the Chernobyl, for instance. And what it really does, it doesn't necessarily give you superpowers. It just kills a lot of cells, and the rapidly dividing cells, things like for hair follicles and stomach lining and eyes, those are susceptible. They're the most susceptible, and so a lot of the signs of radiation sickness, hair falling out, and stomach issues. This is from that, and because of the effects on the GI tract, you don't get the ability to get nutrients and food. So I've never had radiation sickness, and it's kind of like having the really bad case of the flu, from what I've heard. But in, of course, extreme cases, you get death. So for lower doses, though, and we'll talk about the exposures in a little bit, lower dose of radiation can cause cancer, and that has to do with the improper repair of damaged cells. So, but if it's the cells grow abnormally, it can form different types of cancer. So, and these can also then grow into malignant tumors and so on. So, cancer risk, generally speaking, goes up with increased radiation exposure. Although, unfortunately, one of the causes of cancer is actually bad luck. You can just have bad luck, but it's a game of chance. But being exposed to radiation certainly increases your odds. So, and could be some genetic effects. So we haven't quite seen this in humans, but we're still looking. Data is ongoing, but we've seen it in other animals. For radiation exposure, so Curie, a Curie is defined by 3.7 times 10 to the 7 decays per second, and there's also a rotogen, and a rotogen is 2.58 times 10 to the minus 4 coulombs. So it has to do with the amount of charge per kilogram of air. So that's the charge per air, and then we typically do it by rem or gray. So a rem and a gray are about the same. So rotogen equivalent man, and you can look at. So I've had CT scans, for instance, and I ask them what my radiation exposure was and that kind of thing. So you can get them for nuclear imaging. So generally speaking, where you're at, you get 1/3 of a rem per year. So it also depends on where you're at. Like in Hawaii, this is lower because I'm recording this in Hawaii, and there's not a there's not a we don't have radiation, or we don't have uranium in the ground here, so we have significantly less than other things. So, but and because a lot of the exposure comes from radon, but there's still in building materials and various things. So effects of radiation exposure. Well, I should say, first of all, how much radiation are you allowed to get? Normal people, by the U.S. government, you're allowed to get 5 rem. That's allowed per year. If you take a safety class and get certified, you can get 10 rem per year. And you really don't get exposure. You don't really notice anything until 20 rem. It's really more about 25. So 25 rem is when you start to see a physiological effect, and that's about what the dosage of people got in the workers that got in the Fukushima reactor. They were hanging out, and they weren't hanging out. They were working there, and they got a dose of about 25 rem, and they were fine. So, but at about 60 rem, your hair can start to fall out, and after 100 rem, you can get so the vomiting and GI distress, that kind of thing, and then really it gets really dangerous at 200 rem. So I guess as 100 to 400, you really don't want to get to 200. That's when you get that's when it's getting bad. You especially want to keep under 100, and that's in the event of like a radiological attack. So, but that's the risk of radiation. But generally speaking, you tend not to get too much in nuclear medicine. If for bad radiation exposures, it's going to be from nuclear weapons or nuclear reactors, is where you're going to have this level of doses to things. But it's used pretty well. So technetium 99, so you can use it as a bone scan. There's an image of a bone scan. So I've had this done to me actually, and it was an interesting thing. They injected me with a technetium 99, and they were able to image my skeleton. So and it's a beta emitter. So not a beta. I'm sorry. Yeah, it is a beta emitter, but it's also it gives is a metastable nucleus, and it has a half life of about 6 hours. So I was pretty hot for a couple of days, and I also did a gastric study test once. I ate a radioactive sandwich, and I have a Geiger counter, and I was able to track my radiation, and after the next day though it did pass right through me, and I couldn't find any more. So it's pretty good. The technetium, the radiation does go away. So it's pretty easy to do that. So, but technetium can be used for bone scans. So phosphorus 32. So can be taken up by the cancerous tissue. You can image where things are. Iodine 131. Can be used in your thyroid image and also treat. Well, the treatment for thyroid disorders is just to destroy the thyroid. And if you give someone a high dose of iodine 131, can fry the thyroid. So other things, so you can use exposure to malignant tumor from radioisotopes like cobalt-60, and then this just causes damage to the tumor, and then it can help cause your body to flush it out. And this again is a way to do it without doing surgery on the patient. And this is also working with the body's immune system. So your body does destroy cancer naturally. But it's difficult because it's difficult for cancer because it is you mostly, but it's because the immune system is finding like what is it's you don't want your body to attack itself, but it's also your body is like, well, this kind of looks like me, but it's not me. It's, oh my gosh, it's cancer, time to kill it, kind of thing. So damaging that can also help the body along and flush it out, get rid of those cancer cells. So here's a review. Radioactive comes from unstable atomic nuclei. And there's alpha, beta, gamma, and also positron, although positron doesn't go very far. It's actually more like gamma. You can detect radiation by a film device. You can use a Geiger-Müller counter, a scintillation counter. The half-life, that's about the time it takes for half of a sample to decompose. We can use radiocarbon dating, and we typically do this for anthropogenic things that are made from plants. We also date other living creatures like just like animals. We find bones, for instance. You can date them. And also talk about nuclear fission. And this is when a larger nuclei absorbs and a neutron and then splits apart. It's not just uranium-235. There are a lot of other atoms and nuclides that do this. Also, it produces more than barium krypton. That's one of the things it produces. It's a series of things that it produces. So nuclear fusion is when you combine two lighter elements together. That's the energy behind the stars and our sun. Radiation damage, it just rips apart the molecules. It just ionizes them, breaks chemical bonds, and that just causes damage. And radiation usually doesn't give you superpowers. It usually makes you feel really lousy, and enough can unfortunately lead to death. And the radiation, we can use this though. Scalpels or knives, right? They can be used as murderous intent, but scalpels can also be used for helpful surgery. So we can use nuclear radiation to attack things like tumors and organs like the thyroid, and we can do it without actually having to cut into the patient. So it can be a good thing. Here are the learning objectives and the legal. So thank you again for your time and your attention.